Okay, so today we are moved to the chapter 5, and as you see the chapter 5, we have the two topics. The first one is the control volumes approach, and the second is continuity equations. So the control volume approach is very famous for engineer who analysis the systems with some physical property changes. Okay, so as you see, for our chapter 5, the physical property we are focused on the fluid mass. And the chapter 6, we are looking for the momentums. And the chapter 7, our topic is energy. So this chapter 5 is very important. Some ideas will highlight in chapter 5. And the following chapter 6 and 7 just exchange the mass to momentum and change the momentum to energies. So there are no significant difference ideas, but we only exchange the physical properties. Okay, so this chapter is very important if you can fully understand what I mean in these chapters, and the following chapter is quite easy to understand. So as I mentioned in this chapter, our topic, because the fluid are moving. So if you fix this one cross sections, and some physical property will exchange along these sections. Okay, so this chapter we are looking for the mass, and the following chapter we are focused on the momentum and the energies. And but for the engineering problems, we need the tool to analyze exchange in the systems. So what the tool we need, that I mentioned, the control volume approach, is one of the tools to understand any physical property change along some boundaries. Okay, so this is a highlight for the outcomes for this chapter. So first we need to define what is the flow rate. And in this chapter we focus on the mass. So we are discussing the property related to the mass. And as I mentioned, we need the tool to analyze any physical property exchange along different cross sections. So we use the control volume approach. And the following class, I will teach you how to use the control volume approach. And the most important equations is the continuity equations. So this is very important equations related to our fluid mechanisms. So what we need to discuss in these chapters. And finally, if you understand wells, and then you can predict the cavitation effect. So this is our final chapter for this chapter 5. So what is a definition for the rate of the flow? So famous parameters is the volume flow rate. As I mentioned here is Q, and usually we call that is discharge. So you following the sentence showing here, the definition is the volume changes through a cross-section areas. Okay, so you need to define where is your cross-section area first, and then you need to define how many volume changes cross over these sections. and then you need to pick out the how many times the volume exchange. So you have the delta V and divided the delta T changes. So this is our discharge. So the unit is like the meters cubic per second, right? Because how many times you can identify how many volume exchange when you fix one cross-section area. Okay, so that's some oil supply, and then you can control the hole size, and you have a different discharge flow out. And your mouth also, you can control the mouth size, and you can control the air exchange rate. Okay, so the idea, we can following this cartoon figure showing here, and we based on the uniform flow idea. What's the uniform flow? As I mentioned, the uniform flow is anywhere we have the same velocity field. So that means the velocity is always constant values at any locations. So in that way, we consider a cylinder shape, and we know if this is our cross sections. So we have the cross section areas like the pipe, and then you cut the one cross sections, and then you can compute the delta V. For this case, the delta V, that means the volumes of this cylinder's shape. So you have the high is the velocity, the constant velocities, multiply the delta T time intervals. So you have the high in here, right? And if you have the high for the cylinder shape, and you know the bottom area is A, so V delta T is high, and multiply the A, and this is the volume changes passing through these cross sections A. And as we mentioned, the Q discharge is defined by the volume changes divided the time interval. So if you divided the volume by the time interval, and the delta T in here, you can cancel out, right? So finally, you know the discharge is totally equal to the velocity directly multiplied by cross-section area. Okay, so the idea is very simple. If you have the flow velocities and you have the cross-section area, and then you just multiply the velocity by area, and equal to discharge. But this is based on assumptions. The velocity directions is always parallel to the cross-section area, the normal factors. Okay, that means this is your cross-section, and the normal factors of the cross-section is in these directions, right? And your flow coming, this is your flow, and this is the velocity directions. So the velocity directions is always parallel to the normal factors of the cross-section area. Okay? So if not, you cannot define the discharge is equal to V multiply A. Okay? So based on this idea, why the reasons the Q is always equal to V multiply A is because we consider the uniform flow first. And then we consider the flow velocity directions is parallel to the normal factors of the cross-section area. Okay? So if not, So first, we consider different conditions is the non-uniform flow. The non-uniform flow, that means the velocity is the spatial functions. As I mentioned here, this is the piping flow. This is the piping flow, so I assume the velocity is as a function of the radius length. So we have the different radius lengths. The location in here or here, the velocity is not the same. Okay, so in that way, but we still consider the flow velocity, these directions is always parallel to the cross-section normal factor components. Okay, so in that way, we cannot compute the Q is directly equal to V multiplied A, because the velocity in here is not always constant. And then we assume the velocity maybe is a function of the radius. Okay, so as what I use the difference is I use the integration operator in here, and the V will change at the different locations, and each velocity in here acting on the small section cross areas, we use the dA. So different dA, maybe another dA in here, different dA will have a different velocity. So that's why we use the integrations. Velocity at a different location multiply the dA small piece of the cross-section area. And then finally I do the integration, sum of all V multiply the dA. So you can say that the V and the dA is dQ, right? And then finally we integrate along the different areas, and finally we have the total discharge. Okay, so that's why the reason, because the velocity is not the uniform flow, so we need to apply integration operator to process these problems. Okay, so another case, the final ones, because the velocity in here is the vectors, and we know that when we compute the discharge, we need to assume the velocity directions is always parallel to the normal factor of the cross sections. But in that way, in this example, is not the true, because we see that the velocity factors is not parallel to the normal factor directions. So for this case, here we use the dot product. And then we can always, if we use the phi factors, the velocity always apply the dot product with the small cross-section areas. They are always the factors components. And then we apply the dot product operators, and then that we don't need to consider the velocity directions is always parallel to the normal factor, because we apply the dot product operators. So this is finally the general formula we use, because this is for general conditions. We don't need to consider the flow is uniform or not. And we don't need to consider the flow directions is always based on parallel to the normal factors of the cross sections. So usually we will use the final formulas. So totally we have the three formulas. The first one is we assume the flow is uniform flow, and the normal factor of the cross section area is parallel to the flow directions. So we know that we can directly compute the discharge by velocity multiply the cross-section area, right? This is the first we are introduced. And the second, because we consider the flow is non-uniform flow. So the Q, we need to use the integration operators and integrate the V divided, multiply the small area, cross-section area. And the final formulas for the discharge, we use the factors. So we change here is the velocity factors, apply the dot per dot, and then with the cross-section area factors. Okay, so this is the first condition is for the uniform flow, and this for the non-uniform flow. Okay, and the final is we don't need to consider the velocity direction always parallel to the normal factors of the cross-section area. So it's a much general. Okay, so this is very important when we discuss with the volume flow rate. And I emphasize the idea again because we are discussing with the conditions. If you fix one cross sections, and then because your flow is moving, so that at the different time points, there are some physical property will exchange along this cross section. And this chapter we discuss with the mass exchange along these cross sections. But right now our unit is volumes. So as we know, if we have the volumes, we have the volume in here. This is the volume changes with the different time intervals. If we multiply the density, if the Q multiply the density, what is the density? The density, the unit of the density is the mass divided the volume, right? So if you have the Q discharge and multiply by density, and you can change the volume rate to the mass flow rate, because the volume will cancel out, and finally your unit of the mass rate is the mass divided the delta T. Okay, so this is the finally what we want. We are discuss the different time we have the different mass exchange, and how fast it is when we will have the different flow conditions. So this is the finally the parameters will be used, discussed in these chapters. So we call that is the mass flow rate. Okay, so summarize. So we have the volume flow rate, and this is the Q, and usually we call that is the discharge, right? And if the Q multiply the density, and then we call that is the mass flow rate, and the parameter we use the m dot. It indicates the mass flow rate. Okay, so the two parameters are very useful when we discuss the fluid mechanism problems. Okay, so you need to keep it in mind. So, but in real case, usually we trying to understand the mean velocity first. Okay, so what is the mean velocities? And as the formula I showing here, we have the Q, we have the area, and we use the V bar is mean velocities. Okay, so how can you compute the mean velocities? You see here, as I mentioned, the V, and we have the dA, and this is the Q, right? And the Q divided the total areas, and we call that is the mean velocity. We call that is the mean velocity. So the physical meaning is we call that is area weighted average velocities. Why we call that is the area weighted? Because this is the weight, right? And this is the velocity. So we compute the weight, but the weight coefficient is divided by the area size. So that's why we call that is the area weighted. But why we call that is average? Why we call that is average? Because we divided the total area in here. So the first item in here, this is we call that is the area weighted. And why we divided the A 2? Because we call that is average velocity. So we have the weighted in here, and we divided the total areas. So we call that is area weighted average velocities. So ideally, the different flow condition, we have the different mean velocity. So the table summarizes 3 flow conditions, and we look what is the relationship between the maximum velocity and the mean velocity. We take a look the different ratios between the mean velocity and V maxima. Okay, so the first case, we consider the flow is laminar flow in the pipe. The laminar flow in the pipe, as I mentioned, why can we identify the flow is laminar flow or not? So we have a laminar and we have a turbulent, right? And as I mentioned, how can we distinguish two flow conditions? That's based on the Reynolds numbers. And the Reynolds numbers, as I mentioned in here, we have a Reynolds numbers. If a Reynolds numbers high enough, and then we will call that is turbulent flow. If Reynolds number is small enough, and we call that is laminar flow. Okay, I have defined the Reynolds number in our previous class, and if you forgot the formula, you can go back to see the PPT file. And then because the laminar flow in the wrong pipe, and we know that the ratio between the mean and the V maxima is 0.5. But if you consider the rectangular flow and based on the laminar conditions, but the ratio is different, is 3/2. If you are considering the flow condition is turbulent flow and also in the pipe, and you see the ratio is the range, because we tell you the turbulent flow trying to move the flow condition back to the uniform flow. If your flow is uniform flow, so the mean flow values velocity is quite close to the V maxima because of the uniform flow, if it is a uniform flow. So you see the ratio is quite close to the 1. But compared to previous two conditions, one is 0.5 and another is 3/2. So they are totally different. So in these chapters, we will practice how to compute the relationship V mean divided the V maxima for the different conditions. So this is the case 2 in previous slide. The channel flow, this is a rectangular flow. And we know that the answer for the channel flow, the V mean divided the V maxima is, actually we know is 3/2. And this is the pipe flow, is a condition 1 for our previous slide. And we actually know that the V mean divided V maxima is 0.5. But the why? So we need to prove why the different ratio under different conditions. This is our this chapter's very important. The key knowledge is, if you understand how to prove the relationship between the V mean and the V max, and you understand what is the Q and what is the mass flow rate. Okay, so our following examples, if we know the velocity, and because we know the V mean, the mean velocity is the area, total area over 1, right? And we do the integrations, the right hand side is Q. So we have the velocity field and multiply the dA, and we do the integrations. So we need to know the dA, we need to know the velocities, and we understand the total area, what is the total area, and we can process these integration problems. And finally, you need to prove the relationship between the V maxima and the V bar. Okay, so for this, okay, maybe we don't have the time, so because we need to have the quiz. So this is next Monday. I will. We need to practice this problem, okay? And then you see the next is for the pipe flow. So we can prove the relationship by ourselves. OK， 好，那我们今天就先上到这里。